In this lecture, we're going to take a look at a few applications of discrete dynamical systems: absorption of caffeine, absorption of alcohol, as well as the gas exchange model in lungs. We'll start with absorption of caffeine because it's the simplest one. Human body eliminates caffeine at a constant rate, which is why it's the simplest model, 13% an hour. Constant rate means no matter the actual amount. So whether you had 1 cup of coffee or 5, the elimination rate will be 13% of that amount per hour. So let's say you had a cup of coffee containing 240 milligrams of caffeine. How much caffeine is going to be in your system in 1 hour, in 2 hours, 3 hours, T hours? So because we have numbers here, we can simply calculate what it is. If I start with 240 milligrams and the elimination rate is 13%, then what is going to be left in the system after 1 hour is 87% of the actual coffee amount. So we're going to take 240, which is our initial amount, and multiply by 87%. This will give us 208.8 if we're interested in the numbers themselves. What's going to happen in 2 hours? Well, the body eliminates caffeine at a constant 13% an hour. So in 2 hours, we're going to have 87% of what was there in 1 hour. So 80% of this number, which means that 87% of this number. So I can have 240 times 0.87, 0.87 of that, whatever number that ends up being. You notice already that we're seeing a familiar pattern. I have applied 87% to 240 twice by the time I got to 2 hour timestamp. In 3 hours, this factor of 87% will be applied 3 times, and therefore I can simply shorthand write that in 3 hours I'm going to have 240 of 0.87 to the power of 3, and in T hours I can simply state that it's going to be 87% taken T times from the initial amount of 240. So if in T hours my amount is C sub T, then I can easily calculate that in T plus 1 hours, I'm going to have 0.87% of what I had in the previous step. And the solution to this discrete dynamical system is C sub T is the initial amount, in our case 240, times 0.87 to the power of T. Now, this is the simplest system, and that is if you had 1 cup of coffee and allowed it to be eliminated from your body. We can, of course, make this system more complicated by assuming that we can also inject additional amount of coffee, plus some constant D, at some amount of time. This will make our system more complex, and therefore the solution will not be quite as simple. Now, the advice we often hear about caffeine consumption is that one should stop ingesting caffeine around 2 p.m. Is there a possible explanation to this particular timeline? And maybe it comes from how the caffeine gets ingested. So what we can do here is think about half-life of caffeine. Can we use the previously derived formula to figure out what is the half-life of caffeine? Well, our discrete dynamical system equation, the solution of it from the last slide was this. Half-life means I'm looking for the time during which I will have exactly half of the original amount remaining. So I'm looking for when is C sub T going to be equal to C naught over 2. Now, once I have that set up, I can simply solve for T. And notice that I can divide both sides by C naught because I can assume it's not 0. I can then take a logarithm of both sides. So what I will have is that T is equal to logarithm of 1/2 divided by a logarithm, natural ln, of 0.87, which is approximately 4.98 hours. So half-life is about 5 hours. Around 2 p.m., so 5 hours after 2 p.m., you're going to have half of the amount of caffeine, that you consumed. In 5 hours after 2 p.m., we are at 7 p.m. 5 hours after that, we are at midnight. By midnight, we would have gone through 2 half-lives. After 2 half-lives, we only have a quarter of the original amount left. So that means that by midnight, only a quarter of the original caffeine amount will still be in your system. Even if you had quite a bit of it, only 25% will be remaining, which is likely enough for you to be able to go to sleep. What we're going to consider next is the dynamics of alcohol use that gets digested and processed by your body quite differently than caffeine. Caffeine degrades at a constant rate, whereas the amount of alcohol that is eliminated by the liver depends on the amount of alcohol present in the body. So this is a much more complicated process. The larger the amount of alcohol in your bloodstream, the smaller the proportion of it being eliminated. We're going to make some assumptions on what we mean by a drink. One drink will be 14% of alcohol, and that is equivalent to 1.5 ounces of vodka or 5 ounces of wine or 12 ounces of beer. And we're going to introduce some notation. A sub t will denote the amount of alcohol at time t. Again, this is what's going to really drive how the alcohol gets eliminated. R of that number is the rate of elimination of alcohol given the current amount in the system. So we need these two different measures, the amount itself and how fast it eliminates at that particular amount. The following function has been experimentally derived to model what the rate of elimination is depending on the amount of alcohol present. What we can do, of course, is calculate what is the rate given different amount types just to get a feel for how the rate actually behaves. Here's a table when we can record our findings. So once again, let's actually note this here. A is the amount of the alcohol in the system, and R is the rate of elimination. If I plug in 6 into the amount and calculate the rate of elimination, we're going to see that we get 0.9902. If I proceed by filling in this table, here are the numbers that I'm going to get. Now, these values are in percent per hour, which means that if the amount of alcohol in your system is 6 grams, so half a drink, then in 1 hour, your body will eliminate 99% of it. However, if the amount of alcohol in your system is 70 grams, which is quite a bit of alcohol, then your body in 1 hour will only be able to eliminate 13.6% of that. We notice that the smaller the amount of alcohol, the faster the elimination rate, and the other way around. Let's see if we can set up the model to track the amount of alcohol, not just for 1 hour like we did in this table, but for 1 hour after 1 hour, again introducing this iterative nature to our model. First of all, notice that if I have a certain amount of alcohol and it gets eliminated at a given rate, then the amount of alcohol eliminated can be computed as the product of the two. If I have 6 grams of alcohol and 99% of it gets eliminated, 99% times 6 is what gets eliminated. Then the amount of alcohol present is going to be what I have left minus what has been actually taken out. Let's record this in the notation that we have introduced. So as I just said, the amount of alcohol eliminated is the amount of alcohol times the current elimination rate. The amount of alcohol is AT. The elimination rate is R of AT. Note that we actually have a formula for R of AT. So altogether, I can note that this is equal to AT times this experimentally derived formula for the elimination rate. The amount of alcohol then present is the amount at time t minus the eliminated amount. So present at the next stage is the amount currently in the system minus the eliminated amount, which is this big fraction right here. Now, just like in the caffeine example, this is going to be the model if we have consumed a number of drinks and then allowed the body to simply eliminate the alcohol out of the system. But if you are adding additional drinks, then you have to also compensate for that. So this D here can stand for alcohol consumed in between the two time points. So between time t and time t plus 1. We're going to take a look at a few examples where this D takes on different values. So here's our first example, half a drink per hour. So we're going to assume that a student, or any human really, had 2 rapid drinks and then consumes half a drink every hour. So 2 rapid drinks are 28 grams of alcohol, and that is our starting amount. And half a drink per hour is 7 grams of alcohol as an addition to it. Using these 2 pieces of information, we can rewrite our model with the new numbers. So notice that nothing about the first setup actually changes. The initial amount will only affect us at our calculations once we actually start plugging things in, but the constant addition of the half a drink per hour will appear as the plus 7 tacked on onto our overall formula here. Okay, so let's see what happens. I know that we're starting with 28 grams. What about A1? So how much alcohol is going to be in the system in 1 hour? I'm going to plug in 28 for AT or A naught in all the spots here, and then calculate the total amount. My A1 will come out to be 26.2. Then we're going to do the same for A2. We're going to plug this number in the previous state into AT in order to calculate the next state A2, which will work out to be 24.5. In a similar fashion, we can proceed to calculate a few other values just to see what we think the actual trend is. We are noticing that the numbers keep decreasing, and therefore we have a feeling that the total is decreasing, and so the amount of alcohol in the system is getting eliminated. Even though we're supplementing every hour, basically the supplementation is not big enough for the body to avoid eliminating the total amount and decreasing the total amount. Now, how can we figure out really what is this tending towards? So if we consume half a drink per hour for a very long amount of time, does this mean that we will eventually reach 0? Unlikely. Now, what we're after here, of course, is looking for an equilibrium. Now, again, you can do this algebraically, but this is a pretty big formula to deal with and look for a solution for. So what we can do first in order to get some visual confirmation is to draw the graph. We're going to draw the graph of this as an updating function, and here is what it looks like. Remember that for the cobwebbing, the first thing to do is to draw the diagonal. So I'm going to draw the line that goes through the lattice points here. This is my diagonal. What I notice immediately is that I have a point of intersection somewhere right here, which means that I am looking for this as an equilibrium. Now, the starting amount in our example was 2 rapid drinks, so 28. So 28 will sit over here. This was my C naught, and the cobwebbing suggests that we go up to the function vertically, remember, to the function, and then to the diagonal horizontally, to the function, to the diagonal, to the function, to the diagonal. And stumbling in this way for a very long time, you notice that just like in our data, the changes are really small, so it's going to take a while to get to the equilibrium here, but you will be converging towards this as an actual eventual equilibrium. Now, what the graphing method does tell you, especially if you use things like Desmos, so your graphs are pretty accurate, is whether or not the equilibrium is stable or not. If you would like to know the exact value of this intersection point, then the analytic method is the better way to go. So what we're going to do is set up our equation. So the right-hand side of our equation was this one big expression. And remember, an equilibrium means that the next state is equal to the previous state. So both sides get labeled A, or if you wish, A sub t all over the place. Okay, if we solve this equation, we're going to find out that A is equal to 29.4 over 3.1, or approximately 9.5. So this is now my equilibrium. And from the cobwebbing, I can see that it's in fact stable, because if I start above it, my cobwebbing converges towards it. So once again, let's pause here for a second and think about all the tools that we've utilized. We can set up an algebraic equation in order to find the exact value of the equilibrium, and we can use the cobwebbing to tell us whether or not it's stable. Let's take a look at the next example. So the same setup in the beginning, 2 rapid drinks to start off with. So my A0 is 28 grams of alcohol, but now we supplement with 1 full drink per hour, which means that our model needs to be slightly adjusted. My beginning is still the same, A sub t over 4.2 plus AT, but now we're adding 14 grams of alcohol. So if I use this formula to calculate the following amounts, what are we going to see? A1 is going to be 20.2, A2 is going to be 25.8, A3 is going to be 31.1, A4 is going to be 36.2. What we're noticing, of course, pretty clearly, is that the total amount of alcohol in the system increases. That means that the body cannot beat the 1 drink per hour in terms of elimination. How would that correspond to what we're seeing on the graph? So now we have to graph this as our updating function, and it's the same graph but raised a bit, right? So in the previous iterations, it was the same shape but plus 7, so the vertical shift has been 7. The vertical shift is now 14, so this number is going to be higher up. Now, to use the cobwebbing, I still have to draw a diagonal to be able to bounce my initial my states off of it. And again, I'm labeling in order to be able to keep track of where is my function and where is the diagonal. We're starting at 2 rapid drinks, so at 28 over here. This is my C0. Remember the process. We go up to the function and then horizontally to the diagonal, to the function, to the diagonal. And what we notice, of course, is we keep running away from things. Now, here, it's not really clear what's happening off the screen. Will the 2 functions eventually intersect? And maybe there's a stable state here where there is a maximum amount of alcohol that the body will be able to reach or not. This is one of the issues with the graphical method. If we cannot see enough of the graph or know enough of the graph shape, because this function is a pretty complicated looking one, then we're not entirely sure about the points of intersection. That means that algebraically, we're still going to need to solve the given equation and figure out whether or not it actually has any solutions or any equilibria. So setting this to be equal from the present state to the next state, we can solve, and what we find in this case is A is approximately minus 15.1. And that's the only solution. Now, this is not reasonable in context where A stands for the amount of alcohol in the system, which means that there's no contextual solutions, nothing that will make sense for our model, which means that overall we have no equilibrium. Now, that means that the body will not be able to eliminate alcohol out of the system. It won't even be able to reach the maximum amount, right? So the equilibria does not exist. This will continue on this way forever. Now, what if we assume so-called pure elimination? So a student consumes some amount of alcohol and no longer takes in any additional amounts on some time intervals. How long will it take to eliminate the alcohol purely out of the body? So here, our setup is still the same. So my formula still holds, minus 10.1 AT over 4.2 plus AT. Now, the original initial amount is 60, which means that we can now simply plug this number in and calculate the further amounts as we go. Now, what we will notice is that, again, because the elimination rate depends on the amount of alcohol present, if we start with a large amount of alcohol, the progression towards elimination is going to be fairly slow and it's going to take quite some time. But it is decreasing. We're at hour 6 over here, and now is when the rate picks up because there's not that much alcohol left. And then finally, in 7 hours, we're able to reach a negative amount. Now, of course, there cannot actually be a negative amount of alcohol in the system, which means that somewhere in here, there will be none left to speak of. Approximately 7 hours is how much it takes to eliminate 60 grams of alcohol out of the system. Our next application in this section is going to be the gas exchange model. So we've already seen the video on the branching structure of lungs, and it mentioned briefly about how the gas exchange actually happens in the alveoli. What we can consider here isn't necessarily how the actual oxygen gets replaced with carbon dioxide, but generally, if you breathe in air with a certain element and you breathe out some amount of whatever happens in your lungs, how does the concentration of any chemical, including oxygen or carbon dioxide, change inside your lungs? We're going to assume some pretty average statistics for a human. For example, we're going to assume that the lung has volume of 3 liters when full, so on inhalation. We're also going to assume that with each breath, 0.6 liters of air is exhaled and replaced with whatever happens to be ambient air. Suppose that there is some chemical, again, it can be carbon dioxide or anything else like this. Suppose it has a concentration of 2 micromoles per liter inside the lung, and the outside concentration is actually higher at 5 millimoles per liter. So you're breathing in some polluted air, let's say. What is the chemical concentration in the lungs after one breath and then after several breaths? Let's see how this works through the actual breathing in system. At the beginning, the concentration of the chemical inside the lung is 2 millimole per liter. And if we exhale, that concentration itself doesn't change. The amount of air in the lung changes, but not the actual concentration of the chemical. Now, let's think about the total amount of actual chemical in the lung, because between these two stages here, the shape and the volume of the lungs have actually changed. So in the beginning, the total amount of chemical in the lung on the inhalation is when the lung is full. So that means it's 3 liters of the volume times 2 millimoles per liter. So overall, 6 millimoles. On the exhalation, we decided that we exhale 0.6 liters. That means that now the volume of the lung here is 2.4 liters as opposed to the 3 liters on the inhale, which means that at the concentration of 2 millimoles per liter, I now have 2.4 liters times 2 millimole per liter, and overall 4.8 millimoles. Now, what is going to happen to the total amount of chemical as we go from exhaling to inhaling? We're going to take whatever concentration was already in the lung and then add the amount of the air inhaled at the concentration of the chemical that is being inhaled. So the process here now is a little bit different. We're taking in 0.6 liters of the ambient air, and remember that the concentration of the chemical in the ambient air was different than on the inside. So in order for us to calculate the total amount of the chemical inside the lung now, we're going to take our 4.8, which is what's present there now, and we're going to add the amount inhaled, which is 0.6 liters, times the concentration of the outside air. We can, of course, compute this as a number. This, for example, here is 7.8. And now we can fill in the last square of this table of ours that we don't know yet. What is the new concentration of the air inside the lung? So we know that overall there's 7.8 millimoles of the chemical inside the lung. And at this point, at the inhalation, there's 3 liters of the volume. So we're going to take our new concentration divided by the amount of liters in the lung to get the new value of 2.6 millimoles per liter. Now, this is what's going to happen on sort of one exhale and two inhales. But can we generalize this process? Let's try to assign some variables to it. So let's say that I say that the concentration at present is C sub T. Then this doesn't change on the first exhalation throughout. And now I'm going to basically generalize how I've assumed these numbers work for the general concentration C sub T. So the first thing here is all we did was multiply by 3 because that was the volume of the lung. All we did here was multiply by 2.4 because that was the volume of the lung on the exhale. What happened here is we've inherited this number, this 4.8, and this actually stays constant. 0.6 times 5, the amount inhaled and the concentration outside do not change. We're going to assume that the outside air is well mixed and therefore the concentration of it will always be 5, as opposed to a much smaller inside the lung amount. So here we're going to get 2.4 C sub T, which again, for our first calculation simply corresponded to 4.8, plus the mixed outside concentration here. Okay, I'm going to simplify this a little bit. 0.6 times 5 is simply 3, and that's what we get. And then we took this number, and in order to calculate the new concentration inside the lung, simply divided the whole thing by 3, because that was the new volume of our lung. So we had 2.4 C sub T plus 3, all divided by 3, which I can of course also simplify by dividing through to get 0.8 C sub T plus 1. This is exactly what the concentration is now going to be once we make it through the full inhale-exhale step. So our model is C sub T plus 1 is equal to 0.8 C sub T plus 1. Let's see whether we can find an equilibrium and analyze it analytically and graphically.